for lecture in variability basics. And now we're going to focus on the variability interactions in terms of queuing. So any of you are familiar with this queuing theory? Have you heard about queuing theory before? One person? Anyone else? Two persons? Three persons? Okay, so good. Four persons. So all of you, most of you, okay? So queuing notation and measures, so that's good because we're going to see how to apply these concepts to this class. Fundamental relations, we're going to talk about the notation that we use to classify queue systems. So the first type of queue system we're going to study is the MM1 queue. We're also going to talk about the performance measures, systems with general processing, arrival times, parallel machines and general times. And then finally, we're going to talk about the effects of blocking. So when you have some type of blocking happening in your process, specifically for the MM1B and general blocking models. Okay, so we're going to start discussing the concepts of queuing as they relate for the material of this class. So we now turn to the problem of evaluating the impact of variability on the performance measures for a line. And we're going to take into consideration the three measurements that we study at the beginning of the semester, which are the web cycle time and throughput. Okay, so the actual process time typically represent only a small fraction, 5 to 10% of the total cycle time. So basically what this is saying is the time that the part spent on a machine is very low when compared to the time it spent on the process. Okay, so 5 to 10% of the time the machine will be processing this entity or this part, but the rest of the time that entity is going to be doing something else within the process. So the majority of the extra time is spent waiting for several resources. Okay, so you go from this station, you complete the process, now you go in the queue, as you were saying, as we were seeing in our modeling part of the course, that you see you need a queue every time you need to model a resource, because most of the time that part is going to be waiting for that resource to be processed. Okay, so we need to understand the underlying causes of all these waitings. So queuing is basically the science of waiting. What we do in queuing theory is we want to reduce the waiting time and we want to reduce the queues. Okay, so the science of waiting is called queuing theory. And in terms of the importance of queuing, manufacturing plants are or can be modeled as queuing networks. So most of the time these parts are going to be moving from one queue to another queue until they are completed. So queuing and waiting time comprise majority of the cycle time for your parts or your product. So in terms of the system's characteristics, we have an arrival process, a service process, we have a number of servers, maximum queue size. So in one of the labs, you notice that I ask you to stop not to allow more than certain number of parts in the queue. That's part of blocking, because sometimes you don't have enough space to keep all these parts waiting. So you need to have some certain type of criteria or capacity limitation. Service discipline, so you can have a first come, first serve queue, last come, first serve, and so on. Bulking, routing, and many more. Okay, so these are some of the system's characteristics. Okay, so in terms of the notation that we are going to use and the measures that we are going to use, this is coming straight from your textbook. To use queuing theory to describe the performance of a single workstation, we will assume we know the following parameters. Okay, so we know the rate of arrivals in jobs per unit time to the station, and we just discussed that parameter in our previous lecture. So in a serial line without yield or loss or rework, that rate of arrivals is going to be equal to the throughput at each station. The arrival or the average time between arrivals is going to be 1 over this rate of arrivals. This is the arrival coefficient of variation, the number of parallel machines at each station, the buffer size or the maximum number of jobs allowed in the system, and the mean effective processing time, the rate capacity of the workstation given by this right here, and the coefficient of variation of effective processing time. So in order to apply queuing theory, we're going to assume that we know all these parameters. Excuse me. And the performance measures that we are going to focus are the probability there are n jobs at a station, the cycle time or the expected waiting time in a queue, which is CTQ, and the expected time spent at the station, which is CT, queue time plus processing time, the average working process level in jobs at each station, and the expected working process jobs in a queue. And we have some of the relationships between those parameters here. So the expected time spent at the station is going to be the summation of the expected waiting time in the queue plus the effective time. And we also have 2 for the working process. So if we know CTQ, or the expected waiting time spent in queue, we can compute the working process, the expected working process in queue, and the expected time at a station, CT. And you can see that from here. So you need CTQ for CT, and CT is needed for the width, and for the working process in the queue, you also need CTQ. So knowing that parameter will allow us to compute the rest of the parameters. Okay, so before we continue with our discussion in terms of the analysis, you need to be familiar with this Kendall's classification of queue systems, which basically has 3 parameters that I'm naming here A, B, C. A is going to describe the arrival process, B is going to describe the service process, and C is going to describe the number of machines. Okay? So by using this classification strategy, by looking at the parameters that are going to be here in this expression, we can know what type of analysis, what type of system we are studying. Okay? So And this is the visual representation of what I just explained. So A for the arrival, D for the service process, and C for the number of machines. We also, most of the time, use this classification strategy. So M is going to represent exponential distribution, which you are familiar with. Most of the time, we are using the exponential to describe the arrival process. G is completely general distribution, so it's not necessarily a exponential distribution, and D is the constant deterministic distribution. So this one represents that you're going to have the same time between arrivals in your process. So if it is 10, every 10 minutes we're going to receive a part in our process with no variability. Okay, so we're going to start discussing the MM1Q, which basically says that you're going to have an exponential arrival process, an exponential service process, and you're going to have only one machine. So MM1Q. And if you're familiar with probability and statistics, do you remember what are the properties of the exponential distribution? You know what the memoryless property is? No, well, the memoryless property of the exponential distribution basically and is proved to show that if the probability of your next arrival does not depend on what happened in your process before that. Okay, so if you have 10 arrivals, that's not going to be predicting or affecting the prediction of the next arrival that you're going to have. And that's not necessarily true for all the probability distributions. For the exponential, it is. Okay, so that property allows us to do certain type of analysis when we assume that we are using the exponential, or when we assume that the exponential is the right distribution to represent the arrivals and the processing time. Having that property allows us to perform analysis very simple. Okay, and that's what we are studying with this system, because we are assuming that both the arrival process and the service process are exponential, and that simplifies the analysis for the purpose of what we want to get in terms of the equations and the analysis that we want to perform. So one of the simplest queuing systems to analyze is this one, MM1. It assumes exponential interarrival times, a single machine with exponential processing times, a first come, first served protocol, and unlimited space for jobs waiting in queue. So we are not going to have a capacity limitation in terms of the number of items that can be in the queue. So the MM1Q is tractable, and offer valuable insight into more complex and realistic systems. Okay. So for this type of system, again, on the assumption that we are making that this is a very simple system and that it has exponential interarrival times and exponential processing time, we can derive these equations. The width for the MM1 is going to be based on the utilization, right? In CT of MM1 is basically the width for that machine divided by the arrival rate for your system. And in the same way, the average cycle time in the queue is going to be based also on this U and the effective time parameters. And the average width for the system is a multiplication of that arrival rate times CTQ. Okay, and again, a lot of equations here. if you're interested in knowing how these parameters are derived, there's a couple of research papers that explain the detail level how to arrive to these expressions. Again, most of these expressions were derived as a PhD dissertation for the author of the paper, the author of the textbook for the class. So this art is published and we can get access to those papers. But for now, just want to know the expressions and when to apply them, okay? So let's look at this example. Recall that in the briar patch manufacturing example, the arrival rates to the tortillas 2000 was 2.875 per hour, and that makes the inter-arrival time equals to 2.87 jobs per hour. Assume that the time between arrivals are exponential distributed, and in this case that's not a bad assumption. The jobs are arriving from many different locations. Also recall that the production rate is 3 jobs per hour and that the effective capacity is 1.0, or coefficient of variation is 1.0. Since the effective processing time and the coefficient of variation of 1, just as the exponential distribution does, it is reasonable to use the MM1 model to represent this type of machine. Okay, so we're going to use this to start our analysis. So the first thing we can do is to compute the utilization. So the utilization is computed as U equal to 2.875 jobs, and the production rate is 3 jobs per hour, so divided by 3, and this utilization is 0.9583. So we're going to have an arrival process of 2.87 jobs per hour, and we can process 3 jobs per hour. From here we can compute the WIP, and we know that the WIP is equal to U divided by 1 minus U. So in this case, this is 0.9583 divided by 1 minus 0.9583. So it's 23 jobs. What is the cycle time? So WIP divided by throughput. So we know the WIP is 23 jobs. TH, we define TH somewhere here. So what will be the throughput of this machine? So the coefficient of variation, yes, sir. I cannot hear you. The cycle time. Previous one or the next? Yes. So this one does not require the knowing of the throughput. So that's, do we have this TE and then 1 minus U? We have the utilization. Go ahead, sir. Yes. So that's what I was looking for. Okay. So what would be the value for? Yes, that's correct. But what you were saying is correct too. So you should be able to get the same number. Okay. So in this case, that would be 2.875, and that is equal to 8 hours. Okay, but you're right. We have T and we have the utilization, so we should be able to get the same CT. Okay, so now we need to compute CTQ, which is equal to CT minus TE, and in this case is 8 minus 0.333. So this is 7.67 hours. And the width for the Q equals TH times CTQ. So that's 2.875 times 7.667, which is equal to 22.04 17 joules. Okay, so we applied the concepts that were presented on the previous slide to this example, and we're going to continue next time from this point. Any questions up to now? Okay, so I think this is a good place to stop, and we're going to continue on Tuesday, because on Thursday we're going to have our next lab.